Okay, folks, here is the lesson. This is the lesson on 5.5b, which is what you're supposed to be doing over the weekend. This lesson is so easy, it's totally doable to do this without me guiding you in class. Okay, so let's say we have the derivative of tangent of 2x. You should, and this is basically just chain rule over here. Remember, the derivative of tangent is secant squared, and then because this is not a clean x over here, you have to take the derivative of 2x, which is derivative of inside, which is a clean 2. So this is derivative of inside for the chain rule, and this becomes a 2, which they just moved up to the front. Okay? They just moved up to the front over here. Now, the only difference now that we're doing, remember, this is dy. Okay? Let me type it in. This is dy over dx. Okay? The only new thing that they're doing, okay, is they are going to just multiply both sides by dx, okay? So when you multiply both sides by dx, you're going to get dy, okay? All right. And that's it. That's really the main part of today's lesson, okay? And the whole point of this is just to use a different lens in analysis. So here, okay, we're thinking of it as the slope, okay? The slope right here is that. Here we're thinking of this as the change in y equals to this. So here we're analyzing it with the lens of slope. Here we're analyzing it as the change in y. So if we have if we're given an x value and a change in x value, we want to find out what the change in y is. Okay? All right? So sometimes people might refer to this as the sensitivity of y. Okay? So if a little change in x, maybe 0.1, gives you a change in y of like 50, we know that y is very sensitive because a little change in x gives you a huge change in y relative to the 0.1. Okay? But if we give 0.1 here and we have 0.2 for change in y, we can say change in y, or let's say 0.11, we can say that change in y is really not that sensitive because a little change in x gives us also a little change in y. Okay, now I know what some people may think, well, Mr. Chen, how do we gauge what's a little change in y or a big change in y? People may think that this is a big change in y because you're doubling. Okay, I know it's all relative, but I'm just using that easy example for the sake, with the risk of potentially oversimplifying it just to make a point. Okay, we will talk about sensitivity in more detail and what's a big change, what's a small change. Okay, again, it's open for interpretation right now. Okay, now we have a lot of writing over here, but it's actually a really simple concept and it's very similar to what we did before. Okay? Now, so let's say, so you might want to revisit this graph right here after I'm done with the next one. Okay, I'll leave that on this slide. If you need to rewind and pause, go for it. Now here we have a function, okay, and right off the bat, we have a function that looks like this. Okay, if I were to exaggerate this function, okay, it looks like this. Sorry. All right, that's an exaggeration of the function. Okay, but it's a lot more narrow than that, as you can see in this Desmos graph. Okay, now what I'm going to start off doing right off the bat is taking the derivative of both sides. Okay, the derivative, I mean, of this, and I get this right here. I'm just going to jump from here to here. So if you go from here, start with there, I mean, you should understand how to get to dy over dx, okay, right here. And then you just multiply both sides, okay, by dx. This is really kind of unnecessary, that step. You multiply both sides by dx, and you should get the bottom pink right here, okay? Now, here is where sensitivity comes into place, okay? Or what's related to the sensitivity thing I told you before. Now, let's say we have, we're given 1 and 0.01, okay? So I plug in 1 here, I plug in 0.01 there, okay? And I get the change in y, which is 0.42, okay? So, so again, if I plug in 1 and 0.01 into these two, I get a change in y of 0.42, okay? Now, Now, one thing to note is this, okay? What we're essentially doing here is, let's say I have an equation. Let's say I were to write an equation of a line in point slope form using this slope right here, okay, and I plug in 1 for x, okay. Let's say I plug in 1 for x to find out the slope at x equals to 1, and I get this diagram over here. Let me go in blue for my color consistency, and I get this line over here, okay. I get this line over here, okay. That line is supposed to be tangent to the red, but I'm kind of tilting it and not making exact so you can see the example better that I'm about to show. Okay. Now, let's say what it's asking is, what it's saying with the change in x is, let's say I got this equation of a line, okay, at and this point is 1, 38 right here, okay, and let's say I go left 0, so let's say I go right, okay, I change x to the right by 0.01. So if I go up 0.01, excuse me, right 0.01, we calculate that it's going to go up 0.42. So it's going to land us maybe at this point over here. Okay? So if this blue point right here, this blue point is supposed to be a perfect overlap with this red point. If this blue point was 1, 38, let me go blue here, then this new blue point would be, okay, 1.01 because remember, going right 0.01, okay, and it's going to be up 0.42, okay, up 0.42. So again, this blue line is supposed to look more like this. It's supposed to come really close to that red line. Okay, to that red graph, I mean. But again, I'm exaggerating it. I'm tilting it so you can just see an exaggerated version for the sake of understanding the example better. So we can say that, okay, based on this blue line, if we go 0.1, if we go 0.01 to the right, we are going to go 0.42 up, and we're going to get this point. Okay, so this 38.42 is a decent estimation of what happens when you go right 0.01 from the red graph. Excuse me, let me say it this way. This 38.42 is a decent estimation of what the y value is on the red graph if you go 0.01 to the right of this 1, because the blue line is a decent estimation of the red graph. Okay, so again, this 38.42 is on the blue line, which is a decent estimation of the red graph. Okay, so now let's say we want to find the actual. Okay, let's say we want to find the actual red point. Okay, so what we're going to do is this. So let's say we want to find the actual red point here. All right, let me try to make that a little bit bigger. Okay, right here, that actual red point. So that's pretty easy. All you do is, well, you know the x-coordinate of this red point. The x-coordinate of this red point is going to be, let me use red, okay, 1.01. And so we're trying to find the y-coordinate, okay? So I plug in the y-coordinate, okay? I plug in the y-coordinate over here, or excuse me, the x-coordinate of 1.01 into the original function over here, into this, okay, into that. And that's what, let me see if I can fit all this on one slide, okay? So that's what they did. Oh, and that's what they did right here, Okay, let me move this up a little bit. Hold on. I'm kind of running out of space over here. Boom. Let's move that up. Okay, let's move that up. And let's move this up here. Okay. Now, that's what they did over here. They plugged in the 1.01 and they got the 1.01 and they got the 38.42. 1000 whatever. Okay? So again, when they plugged in the 1.01 into here, they got this 38 point. They essentially got this equation, okay, which is what happens when you plug in 1.01 there, and they got 38.42. So I'm going to change this to 38.42 here. Okay? All right, roughly 38.42. Now, again, that's pretty close to our estimation of this blue that our blue line over here got. Okay, it's a little whatchamacallit, okay, because this is really 38.42101. Okay, now check this out. All this is saying right here in the beginning. Okay, so the big picture is that you understand what I said so far, which is like you're 99% there. This is close to that because our blue line is a decent estimation of the red graph. Again, as the blue line keeps on moving up, or let me say this, as x keeps on getting, if the change in x keeps on going to the right, that means the blue line, or let me just put it this way. As we drift farther from this original red point, okay, if we're trying to find an estimation up here, that means the blue line will diverge from the red graph and our estimation becomes less accurate. The closer we're trying to find the estimation to the original dot, the better our estimation be. The farther we're trying to find the estimation, the more the divergence of the blue and the red line becomes. Okay, now all they're doing here, this last 1%, okay, of the problem is this. Okay, they plugged in 1, okay? They basically plugged in 1 into the original equation, okay? They plugged in this 1 into the original equation, okay? And so they plugged in 1 to this original equation and they got 38. Obviously, okay, because this point is 1, 38. Now they plugged in 1.01, okay, into the original equation, and they got 38.42, blah, blah, blah. And so they subtract the two. They basically want the vertical distance between this, okay, they want the vertical distance, and they subtract the two, and they ended up getting this right here, okay? And then what they did was, they found the vertical distance between our estimated blue point, okay, and the 38 earlier. So the vertical distance between the estimated blue point, okay, and this is basically 0.42, which is what we got over here, okay? So all they're saying is that the vertical distance that we estimated, which is 0.42, is pretty darn close to the actual vertical distance when we plug in the 1 and the 1.01 into the 38.42. Okay, again, let me say that one more time. This is the estimated distance, okay, because it's based on the blue dot. Okay, this is based on the blue dot up here. And that is very close to the estimated vertical distance between, the actual vertical distance between this top red point and this bottom red point of 0.42, which they got from plugging in 1.01 into this minus plugging in 1 into this, and you got 0.42. Okay, so that's basically it. Okay, so this graph over here is basically a graph that is specific to this example rather than this general graph here, rather than this general graph here. This general graph and this general graph is a general explanation for what specifically happened here. I just used this specific graph over here. Okay, that's all, folks. Thank you for tuning in.